So the next demonstrator is the AI for Earth observation data project developed in the UCD team. So firstly, Earth observation data, or EO data, as it's known, from satellites, UAVs, or better known as drones, etc., is continually improving in terms of resolution, coverage, as well as accessibility. So firstly, as sensors and instrumentation on satellites improves over time, and also there are new satellites being put into orbit regularly from the likes of national space programs, particularly European Space Agency, ESA, and NASA would be the well-known examples. And there's also many private companies now that are putting Earth observation satellites in orbit. The coverage is improving as well. With the ESA Sentinel program, for example, that's continually mapping every portion of the Earth. And I think the refresh rate is right 3 to 4 days for most points on Earth. So that's quite a new updated refresh rate of data. And there's also geostationary satellites, which are continuously reviewing certain areas. And the key thing as well is accessibility. So a lot of the data, particularly from ESA and NASA, is available free of charge to anyone. So a lot of this data is just being made available. It's accessible. It's sort of open source in a way, and it can be used by anyone. And there's also third-party providers and private companies as well that are providing Earth observation data, which might be from their own satellite systems, or it might be that they've processed in a certain way from some of the other providers. And this is available for a price, but there's an amazing range of data that's available through these providers as well. And there's many novel use cases that are emerging across a range of industries and applications, and some very new types of industries and areas where this has been applied. And many of this is being enabled through AI and machine learning. So one of the things with Earth observation data, particularly satellite-derived data, is it's very large in volume. There's a huge amount of data being generated continuously. It's often very complex. There's multiple layers, multiple different kinds of sensors, and processing and getting value out of that data requires very advanced techniques, which often are in the machine learning and AI domains these days. But one of the problems as well is that applying machine learning to Earth observation is it's very complex, and it requires a combination of both knowledge of Earth observation data, sort of how to interpret that data, what that data means, and even down to maybe certain artifacts in the sensors that's gathering it, which has an impact on what the data means. So it's very specific to Earth observation area, and AI expertise. So if you want to do any machine learning or AI type applications on this, you need that expertise in building those models as well. And this requirement of this sort of two types of quite advanced and specific expertise is often a barrier to companies who could potentially benefit from exploring the potential of this new available data source. So through this, the goal of this project is to develop approaches and tools to make it easier for companies to explore the potential of machine learning powered Earth observation solutions, and particularly in their own areas, their own industry areas, or their own specific niche applications that would benefit them. So to introduce the team, the lead researchers are Anthony, Inder, and CeADAR, and with support from David, who's doing an internship with us at the moment, and Sad on the implementation support. So the company partners on this project are Verisk, Blue Insurance, Creme Global, Munich Re, Siemens, Even Better Value, Version 1, BPI Unitech, and Gamma. So some of these companies are already involved in Earth observation and GIS type work. So just to look at the state of the art. So Earth observation data, it's very commonly used in, and it's been traditionally used in sort of scientific endeavors such as tracking climate change, measuring water quality, disaster management. So these are the sort of traditional use cases and applications of it. However, there's many more commercially focused use cases that are gaining popularity. So these are things in agri-industries, for example, estimating crop production or mapping crop types, tracking subsidence in buildings related to construction or insurance, for example. And another key area is forest resources. So global timber industries are very interested in using this kind of data for tracking forests. So there's a lot of industries and companies that are involved in physical assets, whether that be sort of natural assets or infrastructure, for example. And Earth observation data gives a view on these kind of physical assets. And then there can be value and novel applications from this kind of data that gives an advantage to those companies. But it's still very much a nascent field. So there's a lot of novel ideas that are readily available and new ideas that you see all the time. So in this space, it's very often that we see new startup companies with a very novel idea that no one's thought of before, using Earth observation data in some kind of unique, non-expected way, and creating value from this kind of data. And particularly in terms of machine learning applied to Earth observation data, there's a particular approach, convolutional neural networks within deep learning, which is a specialized architecture for processing visual data. And it can be also applied to many other kind of spatial data as well. And these have been widely applied for image segmentation, face detection, and pose detection in the general image analytics and image analysis sphere. And we're doing a particular focus in this project on using convolutional neural networks in our demonstrator. So to move on to the demonstrator itself, the AI for Earth observation data demonstrator, it's an application that we've developed that implements a novel pipeline for training and evaluating object detection and segmentation models using Earth observation data. So there's a brief overview of the pipeline here, and I think Anthony is going to discuss this in more detail within the demonstrator itself. So essentially it's training a data set, enabling the training of a data set, training the model then from that data set, and then producing the model that can do prediction and inference then on new examples. The key part of this demonstrator, it's designed to be used by non-experts. So there was a lot of work put into trying to hide much of the complexity of model parameter tuning, how the specific architecture of the deep learning models and so on under the hood. So the idea was it's allowing companies maybe that don't have a hugely advanced AI and machine learning expertise or resources in-house to build and develop these kind of models through this tool, allowing them to easily build and train these models and see the output and evaluate them. And again, not requiring a huge Earth observation expertise either. So the pipeline makes it easy to create and generate these data sets from satellite imagery, which, as I mentioned before, a lot of this is open source and easily accessible, along with labeled data. So a company might have, for example, survey data of physical infrastructure that that they own or manage or so on. So this could be things like the location of wind farms. It could be things like the location of particular types of buildings or particular types of infrastructure. And by combining that labeled data with the satellite imagery, this tool can assist, and the pipeline can assist with generating those training data sets, which is in a lot of machine learning applications and in Earth observation as well. One of the major bottlenecks is just having this training data available. So I will hand over to Anthony and Inder now, who are going to run through the demonstrator itself and show how it works.
Yeah, thanks, Oisin.
Yeah, thank you, Oisin. Okay, yeah, so as Oisin has explained, we will go through this demonstrator. I will go through the pipeline that we have been that we have built for this demonstrator, and then Inder will go through. We take you through the demonstrator, the actual demonstration. So basically, in this demonstrator, we focus on addressing two important aspects as far as using artificial intelligence for Earth observation data. One, making easy to generate training data sets. Because now, in order to create a machine learning model or AI application, you need labeled data sets. And for Earth observation, there are plenty of unlabeled data, but then you need to create a label to be able to train the model. But true, as Oisin said, that once you have this data, then how to build up a machine learning model for a particular application, a particular use case. So we created a pipeline which have two components. One, a first data generation pipeline, which make it easy to generate data sets by combining satellite image and the other geospatial data to create labeled data. But the second pipeline is the flexible pipeline, machine learning pipeline, which make it easy now to train and evaluate machine learning model. Of course, once you have a model trained, you can use this model in a particular application, just passing the input, and then it will give you prediction and inference. So starting with the first part, which is the training dataset generation, this will take in the satellite image, and the pipeline allow you to take satellite image from different sources. It can be from public sources like European Space Agency or NASA, or commercial provider like Planet and other sources. So the pipeline is independent to the type of satellite that you might use. So you can use different satellite data. And also it's take in the geospatial data for a particular area of interest. The first thing you need to specify the area of interest. So for example, for this case, we use OpenStreetMap data, which is open source data, to create a label for detecting object of interest from such image. So, but then this could be any other geospatial data that, as Oisin mentioned, it could be, for example, if a company have its own geospatial data for a particular feature of interest, then this can be also used as input. So the pipeline will combine these two, the geospatial data and the satellite image from different sources to create a labeled data set. Now, once you have this, it means you have the satellite image will be an input to the machine learning model, and then this geospatial data will create a label that will be used for machine learning model to train the model. So after this, then we have the second pipeline, which is the machine learning model. Now, as Oisin said that, the challenge of building machine learning model, especially deep learning, it need someone to have experience of searching, which architecture should I use, searching best parameter, tuning different parameter to get best performance. Now, this requires someone with some experience. So we create a pipeline that automate most of the best practice for creating deep learning model, especially for computer vision application, is focused on Earth observation. So basically the pipeline, the machine learning pipeline automates several best practice for training and evaluating machine learning model for Earth observation application. For example, with this pipeline, you can, for example, tune parameter. For example, satellite image comes with different high spectrum. Is multiple compared to other image. It must spectral. For example, you may have several bands. But the question is, which band should I use for a particular application? So the parameter will allow you to, you can use the parameter to choose which band will give me best performance for this particular application. But also it allows you to, for example, compared to other data, satellite image are very huge. So we automate the process of taking, so it means you can just input any image size, and then the model will take care of this using sliding techniques, goes through all the image and then do train the model and do inference to any input of a particular, of any size, irrespective of the size of the satellite image. So this is the machine learning pipeline, of course, which Inder will show you in the demonstrator. And of course, once you have trained the model, you can save the model. You can save them. You can create an API to use in the inference stage. So in the inference stage, that means you have only a model trained, only just specify the area of interest and the satellite image, and then you can get prediction and inference depending on the application. So this is, in short, this is the highlight of the pipeline that we created. And as I said before, and Oisin said that, we tested this, we validate the use case with the pipeline using dataset from OpenStreetMap. but the pipeline can be used for any other georeference data sources. And it can be also used for, and we use data from Sentinel-2, which is from European Space Agency. But as I said before, it can take in satellite image data from any other sources. So this is an advantage. Means now this is offer an opportunity for company to test their use cases for different data sources, of whether satellite coming from different sensors and geospatial data coming from different other sources. So for this time, I'll take this opportunity to invite Inder to go ahead and show you the demonstrator.
Yeah, thanks, Anthony. So for the demonstrator here, what we have done is we have focused only on the inference side of our pipeline. So what we did is we downloaded Dublin's satellite imagery using our data generation pipeline. So to a pipeline, what you do, you send an area of interest, and that pipeline divides that area of interest into small tiles and downloads data for each tile. After downloading satellite imagery, it also downloads the features or training labels from other sites. Like for this example, we have used OpenStreetMap. So we have downloaded features like buildings, water, roads, forest, but as Anthony mentioned, that we can also download more features from not just from OSM, OpenStreetMap, but also from other sources. For instance, if you have your fisheries data, let's say salmon farms across Ireland, you can also add those features here. And maybe things like farms or wind farms, etc. So what we did is we downloaded this data and we trained our model only on Dublin's data. And as Anthony mentioned, our model pipeline also allows you to choose hyperparameters. So what we found out that out of the 13 bands that satellite images have, 5 of those are best for doing object detection. So that was chosen automatically using hyperparameter tuning. Now what I'll do is I'll just show you how this demonstrator actually works. So we have downloaded Dublin's data and we've also downloaded Cork's data here. So you can see map of Dublin here and the ties there, and below it it's a map of Cork. Suppose you need to run inference on, let's say, tile number 14 here. So you just enter the number in the box around here, 14, and then choose the features which you want to detect. Let's say for this tile, we want to detect buildings, roads, and water bodies. So what I'll do is I'll select these and click on Start Inference. So these are big images and the model itself is very big. So it takes around a minute for the inference to run. But a good feature about the demonstrator, and I think it's a feature in all the demonstrators that we have, that you can actually have history of all the inference runs you have previously run. So tile number 14 is what I just tried. I chose buildings, waters, and roads, but not forest. And you can see it's still loading. But what I'll do is I'll load tile from the past, which I had run inference for. For example, tile number 46 here. Again, for tile number 46, I chose buildings, water, and roads, and the inference has been completed here. So I'll click Explore and see what the results of these of the inference was. So this is tile number 46. So you'll see a lot of buildings, a lot of green areas and roads in the tile. And here are the inference results. So on your left, you'll see the ground truth. These are the labels which were downloaded from OpenStreetMap. So there are buildings in red, and you can see there are small water bodies in blue up here. And there here also, there is a water body here also. And the roads are these dotted yellow lines, as the roads are very thin, so you can, they're not very easily detectable, but you can see them here. So to your right, you see the inference from our model. You can see how that our inference is pretty close to the ground truth. And you can see that the buildings are here, which are pretty much similar to your ground truth image. You've detected the water bodies too. We have detected the buildings in these small patches also, and the roads are also very well detected. But to give you a more quantitative overview of how the accuracy is, what we have done is we have also added a table below this, these maps. And these tables show you what are the number of pixels for each feature. For example, for your buildings in the ground truth, you have around 21,000 pixels. And for your prediction also, you have around 21,000 pixels. For water, you have 47 in your ground truth, and in the prediction, you have 50. So you can see that our model is actually pretty accurate here. Just to give you one more example, let's see at a tile from Cork. Let's try tile number 89, which I had run previously. So tile 89 is around here. Here is tile 89. So lots of green areas in this tile, and I think a few water bodies also. And these are the inference results. So for this inference, I had chosen buildings, water, roads, and forest also. But you can see here that only a few roads are displayed in the ground truth. And this is one of the problems we faced during this demonstrator, that most of the labels that we downloaded from OpenStreetMap were actually incomplete. And we had studied methods to overcome this. For example, in this image itself, you can see there are no buildings and no forest labeled. That's not because they're not there. That is just because OpenStreetMap hasn't completed labeling for this area of Cork. So that's one of the other advantages of demonstrators like these, that you can see here that in spite of not having the labels in ground truth, our model can actually detect new labels. So you can see it detected a lot of new buildings here and a lot of new green areas, along with the roads that were already there. In scenarios like these, you can see that this table is not very good, but we know that our results are very accurate because there is no labeling present, no ground truth labels present for that area. So you can see the roads are around 14,000 pixels for roads, and we have detected around 18,000 pixels, pretty close. But for buildings and water and forest, there was no labels present, but we have still detected those which weren't there, but which should have been in the ground truth. So I think, yeah, so this was tile number 14, which we ran in the beginning of this demonstrator. And I think the inference is complete now. So this is tile 14. So you see a lot of buildings and roads, very few green areas on the right, the top right and top left. And oh, there's a river too. So if you see the river here, and you'll see that there are a lot of buildings and a lot of roads here, and there are buildings in patches also here. And if you look at our prediction here, you'll see we detect a lot of buildings around, and we also detect this river, the water body which we had. Looking at, again, the number of pixels, you see pretty close again for buildings, close to 92,000 and 94,000, 2,000 close for water, and around 22,000 and 23,000 for roads. So again, like you'll see, we get pretty good results for most of the tiles. In fact, the data was only trained, our model was only trained on Dublin's data, and we added Cork just to see how our data generalizes. But you know, the terrain of Dublin and Cork are very different. So if you train a model on Cork, the results will be better on Cork, I guess. So just to wind things up here, the last thing I would like to say that though this demonstrator, you know, things are very limited, that we have only Dublin's and Cork's data, and we have only these 4 features. But our pipelines here are very flexible in terms of adding more features, not just from OpenStreetMap, but also from various other sources. And in fact, our satellite imagery is also very flexible in the sense that you can download data from multiple satellites, and you can just enter any area and it will do the job for you. I think I'll conclude from here, and I think I'll hand over to Oisin for the next demonstrator.